So good afternoon, everyone. I'm Anantha Chandrakasan, Chief Innovation and Strategy Officer of MIT and Dean of the School of Engineering. Welcome to this special distinguished EECS and RLE seminar. It is my immense privilege to be here with you, introducing our distinguished and dear colleague, Al Oppenheim, Ford Professor of Engineering in EECS, a member of RLE, and an affiliate of MIT Lincoln Labs and the Woods Hole Oceanographic Institution. Professor Oppenheim's impact in the field of digital signal processing, or DSP, can't be captured in this very brief introduction. He's truly one of the pioneers in digital signal processing. His fundamental work in signal processing has had far-ranging applications in areas including speech processing, compression and recognition, image and video processing, artificial intelligence, and communication systems. He co-authored the seminal textbook, Discrete Time Signal Processing, which has been used widely as both a teaching and research tool. Of course, I have the orange edition of that book that I'm still waiting to have signed. Professor Oppenheim has been a valued member of the MIT faculty since 1964. Prior to that, he received his bachelor's, master's, and doctoral degrees from MIT in electrical engineering. We didn't have a computer science at that point. Over the course of the past 6 decades, his contributions as a faculty member, advisor, mentor has simply been astounding. I was so lucky to have Al as one of my mentors when I arrived at MIT 30 years ago. Professor Oppenheim has been recognized with numerous awards and recognition over the years, as you would expect. And just to share a few, he's a member of the National Academy of Engineering and an IEEE Life Fellow. He's been recognized from IEEE with a number of awards, including the IEEE Kilby Medal, the IEEE Education Medal, and the IEEE Centennial Award, just to name a few. He received an honorary doctorate from Tel Aviv University. Finally, he's been recognized internationally as a Guggenheim Fellow in France. I'd go on with many of his achievements, but for now, please join me in warmly welcoming Al, who will present his talk on signal processing. How did we get to where we're going?
Thank you, Anantha, and thank you everyone for coming here on this beautiful day at the beginning of a long weekend. And too bad, in some sense, that the shades are down, but they prepared me for that because they gave me 2 laser pointers, one to point at the screen, and the other to kind of single out anybody who seems to be falling asleep. So, as you know and can imagine, this talk is about signal processing. And signal processing has a really long history. It goes back, I guess you could say it goes back millennia, because in one form or another, there have always been signals, and they always have needed to be processed in some form with some type of equipment, whether it's animals processing them or electronics processing them or mechanical systems or whatever. Now, I'm not going to go back that far. What I want to talk about is kind of when the era of digital signal processing started. And in other words, the use of computers for signal processing. And so that era was coincidental with this era. Right around the time that Elvis Presley was in its heyday, digital computers were at a stage where they were accessible enough, fast enough, and you could, I mean, this would be a joke to say, but small enough so that you only needed a very large room or warehouse to put them in. So back then, the basic idea that was happening with digital computers and signal processing was that the accessibility of them was because there were the computers that were developed quite typically for the military, and you could not do real-time signal processing with them, but there were many application areas where data was collected that was very, very expensive to collect, and particularly in the geophysics community. And then once the data is collected, offline, you could process it, obviously, in non-real time, take hours and hours to process seconds of collected data, and do meaningful things from them. So that was one of the typical kind of things that computers and digital computation was being used for in the context of signal processing. Another one was simulation. So the thought was actually ludicrous that you would actually want to really process your signals in real time with a digital computer. For all kinds of reasons, that would be ludicrous. But a lot of analog systems for signal processing were very sensitive to the parameter settings, what the resistor values were, what the inductor values were, et cetera. And so the basic idea was simulate the system on a digital computer and determine the best choice of parameters, and then actually build the system to run in real time. And there was a lot of interest in this in all kinds of contexts, and I'll talk about one of the contexts in a bit more detail in a while, but there was a lot of interest, for example, in the telecommunications industry of using digital filters to determine the parameters for analog filters for the switching system. And there are lots of other examples of that. So, and as I point out at the bottom here, it wasn't really until got to figure out the right button here. Yeah, it wasn't really until the late 70s and beyond that you started to see digital microprocessors being designed and used and built for signal processing. So the activity that was going on in kind of the 50s and 60s, and there was a lot sort of MIT related, and I'll talk some about a number of these people in a minute. But for example, just to mention Anders Robinson and Sven Freitel, they were the name of kind of their laboratory was the Geophysics Analysis Lab. I think that's close enough to what it was. And of course, the geophysics industry was very much involved in using digital computers to do offline signal processing. And a little later, I'll talk about a number of these other people. Now, also a lot of DNA was at Bell Laboratories. Jim Flanagan, in his speech group, was working on speech compression, speech processing. Jim Kaiser, who was one of my mentors at MIT, he was in the electronic systems lab and control systems. And Lincoln Laboratory, he was very involved in the development and use of digital computers for digital switching, which required the design of digital filters, which weren't really practical yet, but that was kind of the research. And then in Europe, these are the people that I'm the most familiar with. And I would say in those early days, probably I would say most of the focus in the United States was somewhat MIT centered, or at least had a lot of MIT DNA, and in particular, Course 6. Okay, now I'd like to show you next the kind of technology that was typically being used back then. So Robinson and Treitel in the geophysics laboratory were using Whirlwind. Whirlwind was a computer that was developed in the electronic systems lab, which is the precursor of LIDS. So sort of LIDS DNA or Whirlwind DNA is in LIDS, vacuum tube computer. And I don't know if any of you have seen in the Computer Museum a piece of Whirlwind, but if you look at that piece of Whirlwind, what you're seeing is vacuum tubes. And of course, that's how Whirlwind was built. And very, very sophisticated computer, as you can tell from these numbers. And then at Lincoln Laboratory, TX0 was built as an experimental computer to be a transistorized version of Whirlwind. And here's a picture of the TX0. TX0 is the first computer I ever learned to program on. And interesting, you can see here 16 switches. That's the way you got the thing going. You put in a set of instructions. And then, of course, you could program it so that it would read the paper tape that is loading up the memory with the rest of the stuff you want to load up. And then also at Lincoln was built the TX2, which was a more powerful version of TX0. So very sophisticated computers at the time. Remember, 100 years from now, when I give this talk again, I'll be talking about very sophisticated computers at this time. So obviously things move on, but just to give you an example of the sophistication, this is a module from the TX2. And I had to check and be careful that it doesn't actually have the property sticker on it anymore, but there it is. That's two flip-flops. And these cans are individual transistors. And that's pretty incredible that a transistor can be that small. You know how many transistors there are in an iPhone? Well, the number keeps going up, but roughly speaking, the last time I checked, it's like 18 billion transistors in an iPhone. Now here's something really true story and kind of amazing to me, and I chuckle about it every time I think about it. So I was showing this picture at a talk in Greece last spring, and I had forgotten to turn off my iPhone. And all of a sudden, I got a call. And it's not that I heard my iPhone ring, because a friend had called me. She was talking into her iPhone in the States, and it went up to the satellite, and it came back down from the satellite into my iPhone, and then through Bluetooth into my hearing aids. And of course, nobody in the audience could see me. It wasn't like I was holding my iPhone up to my ear. Oh, it's only 2 transistors. And I had to stop the talk, because I said to myself, if I, in the 50s and 60s, had claimed that something like that would be possible, literally, I'd be put in a loony bin. So it's, of course, an indication of how technology has advanced and continues to advance. So now what I'd like to do is zoom in on kind of the origins of DSP for me. And I use this slide a lot. You can use this slide for almost anything, because the axes aren't labeled. But in particular, the time that I would sort of focus on, which was the time of Elvis Presley and the 50s. And you know, I have to say that many, many times people have remarked to me, Al, you know, you just seem to have been in the right place at the right time. And I smile and kind of agree with that. And of course, the time was the 50s. I was just moving from undergraduate to graduate school. The places for me were, of course, the MIT campus as an undergrad and then as a grad student. And then a number of years later at MIT Lincoln Laboratory. And so my involvement in DSP kind of focused very much around the involvements that I had in these 2 places. And then I happened to have the good fortune of being around an incredible set of people. So Amar Bose, and I'll say a little bit more about these in a while, but just very quickly, Amar Bose, who is my doctoral thesis advisor, Tom Stockham, Ben Gold, Charlie Rader. So let me ask, how many of you know who Tom Stockham is? How many of you know who Ben Gold is or was? Yeah. Well, and Charlie Rader and Ron Schaefer's name you might know a bit better because of the book that he and I co-authored. But I am going to take the time to talk about these 3 just a little more in a minute. But let me just kind of quickly run through what the timeline was for me. So 1964, I completed my doctoral thesis with Amar Bose as my advisor. I happened to be his first TA when he took over the circuit theory course, and that was an incredibly fortuitous event for me. Tom Stockham, who I'll talk about a little further in a minute, was on my committee. He had just come back from the Air Force. And then in 1964, when I finished my thesis, I joined Ken Stevens' speech group because what I saw was speech as an incredibly special application of my doctoral thesis. And I worked very closely with Tom Stockham on that, and also Ron Schaefer. Then I had a number of pieces of incredibly good fortune. So one of them was, there was this kid from Nebraska. He actually had some difficulty getting into the graduate program here. And then when he finally came, he had some struggles with his oral exam to get into the PhD program, and he was kind of wandering around. Tom Stockham introduced me to him. Ron was and still is about 4 months younger than me. And he was my first doctoral student. That was pretty much the beginning of the start of my research group. And as you know, and Ron and I have continued a very, very close friendship and collaboration. I mean, people have often asked us, they asked both of us, how did your friendship get maintained after you struggled through writing a book together? Actually, 3 editions of the book. And the answer is, with each edition, the friendship just got stronger and stronger. Now, the next piece of incredibly good fortune for me was that Ben Gold, who was a research scientist at Lincoln, came to MIT as a visiting scientist in Ken Stevens' group. He and I connected up. He was very interested in my doctoral thesis and the work I had been doing. And Ben became one of my most significant mentors. I'll say more about Ben in a minute. Now, around that time, it wasn't clear to me that I was really on a path to tenure. And I had been interacting with Tom Stockham and Ben Gold, and Tom had moved to Lincoln at the time. And I decided that I wanted to take a leave of absence from the faculty and go out to Lincoln and work with Tom and Ben and another person out there, Charlie Rader. So I took this 2-year leave of absence from MIT, and they were working on what they kind of called digital signal processing. And for the most part, people weren't paying much attention to what that was, because it required large computers to do the signal processing, and that's really not a very practical thing. And so we were like kids in a candy store. And literally, the way I felt was kind of was sort of depicted in this slide, which is, it's not that we were sort of problem-driven, we were kind of idea-driven. Just, have this idea, and that's what I'm going to do. I'm going to play with it. I'm going to rub these 6 together. And that was just an amazing experience for me out at Lincoln. So then in '69, after the 2 years at Lincoln, I returned to MIT, started the DSP course, and wrote lecture notes. Ron joined me as a co-author, and that was basically the first book that we wrote, which Anantha says he has a copy of that first book, which had an orange cover to it. And it's gone through quite a bit of revision since then. So now what I'd like to do is zoom in on 3 people that I've already mentioned: Tom Stockham, Ben Gold, and Charlie Rader. And I think it's very, very telling and not surprising when I asked how many of you have heard of Tom Stockham. Not really. I mean, I think 1 or 2 people raised their hands. When I mentioned Ben Gold, same. And what about Charlie Rader? Did you ever hear of Charlie Rader? Yeah, okay. But a couple of people from Lincoln raising their hand. Yeah, so Tom he'd come back from the Air Force. He had been a student of Ernie Gilliman's. Now, I gotta ask this question. How many of you know who Ernie Gilliman was? Yeah, actually a few more people, yeah. But, I mean, Ernie Gilliman you could almost say, the EE department back in a certain era. And tremendously powerful force. But Tom was an extraordinary teacher. He was a winner of the Goodwin Medal. And he was just incredibly amazing at taking complicated things and making them simple. Actually, that brings to mind a quote that I made up that I really like, and Tom just makes me think of this, which is, the role of a magician is to make simple things appear mysterious. The role of a teacher is to make mysterious things appear simple. And Tom was a magician at making mysterious things appear simple. So Tom was on the faculty for several years, and then went out to Lincoln Laboratory. And then from Lincoln Laboratory, he went out to the University of Utah. Now, he was, when he was on the faculty here, he was working with Amar Bose. His signal processing revolved around restoring old recordings and modeling room acoustics, which is something that Amar is very interested in. And Tom was doing this with the TX0. I don't think that's Tom, but he was initially doing the work with Amar with the TX0, and then when he went out to Lincoln, he continued that work using the TX2. And among Tom's many sort of signature contributions in audio was his work on restoring old Caruso recordings, and RCA actually produced a whole set of his recordings. Something they didn't actually produce for sale was a very interesting piece of work that Tom did with a student at the University of Utah, which was removing the orchestra from a Caruso recording. The idea, in principle, being, well, then you could dub in a new orchestra. And that's one of the things I like about this slide, but another thing that, and any of you who have heard me give a talk with this slide before, I've heard this line before, but I just can't resist saying it again, that if you look at Tom and you look at a picture of Caruso, there's an eerie resemblance. Which brings to mind the notion that you better be careful about the problems you pick to work on, because you might start looking like them. And I think to some extent, all of us have sort of gone through that process. Now, Tom, for his work in audio, is universally recognized as the father of digital audio. He really is the father of digital audio. A lot of people don't know that, but it is a fact. And he's very widely acknowledged for that and applauded for that. He received an Emmy, a Grammy, and an Oscar for his work. Tom Stockham was a really, really special person. Another really special person, and by the way, Tom was one of the pioneers of DSP. So this is Ben Gold. And I love this picture of Ben. Somehow this picture of Ben captures the twinkle in his eye, the soft, warm smile. Ben was an incredible mentor to me. And he was working at Lincoln Laboratory on speech compression. And so the idea with speech compression, roughly, vocoders. A vocoder, roughly, is a filter bank. But the quality of the speech that you got due to the compression is very, very dependent on exactly the cutoff frequencies of the filters and the bandwidths of the filters, et cetera. This is a picture of the analog vocoder that he was working on along with some other people. And it's transistorized. The inductors were hand-wound inductors. Hand-wound because the parameter, the inductor values had to be pretty precise. And Ben was working with another engineer there, which is Charlie Rader. Charlie is an incredibly inventive, unusual guy. Very creative, very inventive. And I really remember when I was out at Lincoln for those 2 years, and after, because I continued my interaction with Lincoln, when Charlie would walk into the office, into, let's say, my office, and say, Al, I had this thought. Early on, the reaction was, Charlie, don't bother me, I'm doing important stuff here. But very quickly, what I learned is when Charlie said something like that, you wanted to pay attention to it because it was very much out of the box. And I know some of you here, I mean, certainly Tom has met Charlie, and Charlie has come to some of our group meetings over the years, and when Charlie starts talking about the ideas that he has, I say, whoa, how did he ever come up with that kind of an idea? Yeah. Now, when Charlie and Ben and some others at Lincoln at the time were working on these vocoders, as I indicated, to get the parameters right, you really have to do offline simulation. And the offline simulation, it might be an hour to process a second's worth of speech. And what they really wanted to do was have a processor that would basically be a simulator, but it could simulate in real time, in other words, at audio rates. So they built what was called then the fast digital processor. You know why it's called fast? Because it's fast. So here's a picture of it. It was really, really great to work on it, work with it during the cold winters because it generated a tremendous amount of heat. And but this is what it took to do real-time signal processing at audio rates. And so as you can imagine, back in that era, people laughed about sort of the concept of real-time digital signal processing. Really? Why in the world would you want to do that? But as another pioneer of DSP put it, DSP is a discipline that allows us to replace a simple resistor and capacitor with two anti-aliasing filters, an A to D and D to A converter, and a general purpose computer array processor, as long as the signal we're interested in doesn't vary too quickly. And that was the viewpoint. As a serious statement, it was considered ridiculous in the 50s and 60s to imagine that you're going to do real-time digital signal processing. Now, as time went on, there were a bunch of events that happened. The field kind of continues on, and actually many sort of big bangs that happened that made digital signal processing more and more practical. One of them was this paper. Now, I'm sure everybody here knows the Cooley-Tukey paper. Well, they don't know the Cooley-Tukey paper. They know of the Cooley-Tukey paper, and it was published in a mathematics journal. Basically, sort of involves taking the DFT matrix and breaking it down into outer products of smaller matrices, and then you take the smaller matrices and outer products of those, and the paper was written in a very, very sort of formal way. Jim, who I knew very well, was very sort of humble about all this, and he likes to tell the story of when the paper was published back in those days. When you had a paper published, you then could order a certain number of reprints to give away to your friends or your family, or, you know, assuming somebody's going to ask for a reprint of it. And I remember Jim telling me that he ordered the minimum number of reprints because why in the world is anybody going to be interested in that? I mean, what would possibly be the practical application for something like that? Now, just like the wheel and reinventing the wheel, well, yeah, before I go into that, one of the things that made the Cooley-Tukey paper hard to understand, it was very mathematical. And then a couple of magicians came along, and they decoded that paper into what I'm sure anybody here who has ever taught the FFT, used the FFT, programmed the FFT, they think of it in terms of this basic flow graph, which Tom and Charlie came up with, basically as a way of explaining what the Cooley-Tukey paper was about. Now, I was about to say before that just like the wheel could be reinvented many times, and the FFT was reinvented many, many times. And for those of you who have never looked at this paper by Don Johnson, Sid Burris, and Mike Heidemann, it's really worth reading because the takeaway from that is not that necessarily that, well, these were the other ways that the FFT was invented. I think an important takeaway from that is nothing's new. Pretty much anything that you come up with now has been there before in some other form. It's just that it was not important in that form, or nobody knew about it in that form. I remember reading the story of how totally useless matrices were thought it was thought that matrices would be. I mean, but it was a piece of mathematics. It goes way back, and things take on a new kind of relevance. So another piece of the Big Bang was when Ben and Charlie wrote a book in 1969, which was really the first book on digital signal processing. Tom Sockham and I wrote chapters in that book, but it was the exposition of digital filter design, the FFT, and what they were doing in the context of these in speech processing. Whoops. I knew that would happen. This isn't my clicker. And I was debating about whether to use my clicker or their clicker. I was afraid that's the kind of thing that would happen. But anyway, yeah. So Ben and Charlie wrote this book, and it was the first real exposition of digital signal processing in a form that made it very teachable. And I just incidentally point out that obviously the story doesn't end with the FFT. The story goes on in signal processing and DSP to lots of additional algorithms, fast algorithms, efficient algorithms that have been developed. So another piece of the Big Bang is, I guess I don't want to say the invention of the speak and spell, the production of the speak and spell. And you could say, well, why would a toy like that be such an important part of the Big Bang? And what was going on at TI was starting to think about DSP processors, and in particular the TMS 320 series. And they had sort of had a gap in their engineering time, et cetera. And I remember Dick Wiggins telling me the story that they said, well, why don't we just build a chip that does speech synthesis? And let's see if there could be a market for it. And indeed there was. The speak and spell is based on the math of linear prediction using the Levinson recursion and doing the speech analysis offline. But doing the speech synthesis in a chip that they very specifically designed, which is the speech synthesis chip, which implements the filter, which is what's used for the speech synthesis, in a form called a lattice form, which was something that just naturally came out of the linear predictive coding. And this caused quite a stir, not just because kids loved it, but because NSA got really upset and concerned, because they had been working on linear predictive coding, real-time linear predictive coding for speech coding, basically for security reasons. And I remember somebody at NSA describing to me the process you have to get approval for this and approval for that, and how many years it would take to get everything checked off. And these guys at TI did this in, I think they said 3 or 4 months. Okay, so as you can tell, I like this slide. And I returned to it because the question you could ask is, where are we now? And of course, we know where we are right now. You're all here. This is 2024. 2024 is right here. And some amazing things are happening. But you have to be very careful in trying to predict the future, which I'm not going to try to do. But I may suggest some of my biases about the future. So, and I remember this phrase, as Isaac Asimov said this at a signal processing conference, actually. And there's a lot of wisdom in it. And so don't hold me to anything I say, and I'm not going to say anything very dramatic anyway. But what clearly we all know, I mean, we all see it, is that the list of applications of signal processing, and let me pause for a second and say, I tend not to use the term digital signal processing as much as I used to, because who knows what's digital and what's analog. And now you see systems where you can't even tell where the interface is between the digital and analog. So what I'm really referring to is signal processing. And of course, this is just a short list of applications, and the applications keep growing. And of course, it's not signal processing like in the old days. It's often in collaboration with machine learning and data science. Now, when I put this slide together, what I wanted to do was get a Venn diagram. And I started to do a Venn diagram of, and the best I could come up with was something like this. In other words, it's kind of a moving target. Now, the other thing about the Venn diagram is a lot depends on who you talk to. So you talk to some communities and they say, well, yeah, the Venn diagram, and of course signal processing is a subset of whatever. Or you talk to signal processing people and they say, well, of course, machine learning is basically, and you can make up lots of different ways of telling that story, and it depends on what religion you are. It depends on how important branding is. Depends on how important territorial thinking is. But clearly, the collaboration between signal processing, machine learning, data science, and lots of other things is what the future is all about. But I kind of want to return to sort of something I've alluded to, and in fact the way I sort of started my talk out, which is signal processing, has it had its heyday, and is it kind of over? And the answer is, of course not. Of course not. And the way I tend to like to summarize that is there will always be signals. They're always going to need processing. And there's always going to be new mathematics and technology to implement the processing. So signal processing is never going away. Signal processing will take different forms in collaboration with other fields, and that's absolutely the way that it should be. But fundamentally, there will always be signals, they'll always need processing, and there will always be new mathematics and technology for implementation. So the final point I want to make is, did I say I like this slide? I think I did. So back in the 50s, when people, well, now, sorry, not back in the 50s, now, when people say, Al, you just seem to have been in the right place at the right time. My frank and honest answer to that is that all of us always, every minute of every day, are always in exactly the right place at the right time and around the same people, of the right people. The question is, do we recognize the opportunities in front of us? Thank you very much.
Thank you, Al, for that amazing presentation and for sharing your perspectives and history of signal processing. So I'd like to open it up for a few questions, so we could pass this mic around. Okay.
First off, thank you, sir, for an outstanding and illuminating historical tour of the field of signal processing. I was quite fascinated by one of the charts at your conclusion, which tried to bring together signal processing with machine learning and data science, right? I have the following question/observation. Signal processing is built on sound, common sense, firm mathematical principles, and a realism grounded in the physics, right? However, the other two, I'm not so sure. Again, this is due to my own limited knowledge, okay? Because everybody professes deep learning. I only do shallow learning, right? So I understand the signal processing from my shallow learning perspective, but I'd really like to get your opinion, sir, on some of the gaps that exist in these other two domains, which could benefit from the insights that the signal processing community has provided. Thank you.
Now, you're going to have to
Yeah.
interpret that, because
So I think that sort of the signal processing has a lot of grounding and fundamentals.
Right.
While the other two fields, data science and machine learning. What could you learn from signal processing that could be maybe applied into these different domains and
well, I
the
mean,
rigors of signal processing, I guess, right?
I'm sorry?
Signal processing is more rigorous in many ways, while machine learning, you can say that it's a black box.
Well, so the analogy that I kind of like to draw when I think about deep learning and signal processing, deep neural nets, and you kind of run a deep neural net based on training data, and it magically is able to separate out identifying a cat from a dog. And that's amazing. The analogy that I kind of like to draw is the difference between theoretical and experimental physics. So an experimental physicist goes into the lab, he does some stuff, makes a measurement, and he sees something happens. And that's amazing. The theoretical physicist wants to know, why did it happen? In other words, what are the basic underlying principles? So actually, one of the things that's going on in the signal processing community right now goes under different sort of sets of words, but one is unrolling, which is you do something amazing with a deep neural net that it recognizes a cat from a dog. So now you have an existence proof that there is a way that you really can recognize the difference between a cat and a dog. Now the challenge is, what is it that the neural net is doing? So I think that that a lot of the mathematics, signal processing tends to utilize the mathematics often much earlier than machine learning tends to do. Data science obviously uses a lot of mathematics. So I don't know if that touches on the question,
I
but
think that's
yeah.
perfect. And I know there's a lot of work going on here at MIT on understanding how neural networks
Exactly, yeah.
If we could pass the mic over here.
I need it. Quick follow-up to that question. I had a debate with a friend that when I went to MIT,
Please use the mic.
when I used 6003 and 6341 and 6432, I felt like it was this very rigorous theory. And the friend at Lincoln said that's because back then, that's when everyone was just writing textbooks about that, and you were just seeing kind of the early thoughts that they had coming together. Did it feel the same? Was there that experimental side where you were doing things that you didn't really quite fully understand, and then later on you tried to explain them, or was the pathway different at the time?
So I guess the theory follows the practice, or
That's an important and interesting question. And one of the things that came up at the last big signal processing conference I was at was how many people who were practitioners and using, for example, machine learning, that was part of what they do, what part of their job, is they were saying that now they're going back to understanding the fundamentals because they see what the importance of the fundamentals are. My own view, but this is always an issue in education in general. Do you first teach like the basics without a practical motivation, or do you try to get people excited enough to then see the need to go back and learn the fundamentals? I think the art there is teaching the fundamentals in inspiring ways. My own view of education is you should really teach the fundamentals before people get develop bad habits as they become practitioners, and then they've got to break those bad habits. That's my own personal view.
Great, thank you.
Al, that was a great talk.
Thank you.
I'm wondering what challenges and obstacles you faced during this wonderful journey that you described, and what wisdom you might give to our current students about how to overcome these kinds of challenges as you explore a new field.
Yeah, so I can answer that in two very different directions. So one direction is the issue of, related to what I said before about fundamentals, and really getting the fundamentals down right and not getting seduced by the short-term gratification of writing code and having the code work. Understanding the math is important. Let me give you a very different kind of answer to that question, which is along the following lines. It really is important to believe in yourself rather than to believe that what maybe the majority of other people are telling you is the right thing to do. I would say I was just very fortunate that as I was working with Ben and Charlie and Tom, they were passionate about what they were doing, and I was passionate about it. But for the most part, what we were hearing from other people is, this is ridiculous. And so I think that's an important element of it is, if you're passionate about something, pursue it.
Other questions?
No, you can't buy those two flip-flops that I have here.
They're too expensive.
I'm not sure I'm the second oldest person in the room, but I took Al's course something like 49 years ago, I think. Or something. What I wanted to ask you, Al, is today, when it comes to signal processing, is signal processing, are advancements being held back by hardware, or is the hardware technology so advanced that you're limited by other techniques and mathematics?
So what you're asking is whether advances are being held back by hardware?
Or the reverse?
Well, there are things that you'd like to be able to do that maybe the hardware can't do. That's one thing. But I would say, hardware is going to advance. So, you think of quantum engineering, and there's going to be hardware of that type. There's going to be hardware in photonics. There's going to be hardware in biology that will naturally sort of advance what we're able to do. I would say it's the mathematics that is, in my mind, the rich playground for future signal processing. Math is hard, and us who's laughing, Joel's laughing, but why why are programming classes so much more popular than fundamental math classes? Well, you get a very quick feedback in programming that you don't get in math. And math is hard. I remember, and I'm not going to say who this was, but this is a very good friend of mine, and this goes back years, and he's in AI, and this is years ago. And he and I were collaborating, and he said, Al, trying to learn signal processing is like chewing on broken glass. He might even be in here, I don't know. But
Al, you had a statement about FFT and comparing to Moore's Law. You want to repeat that, like the...
well, I guess I didn't say that.
Yeah, I think you did to me. So that, you know, FFT sort of was equivalent to many generations.
Oh, yeah, no, this was somebody at Lincoln Laboratory that actually drew a graph of the advancement that you get out of the FFT as n increases as compared with Moore's Law. I mean, the FFT was amazing. And if you go back and read that paper by Don Johnson and Sid Burris, you're going to say to yourself, well, why didn't I think of that? Or, even more so, you hear this on occasion, not with the FFT, but sort of with any kind of breakthrough. Oh, I kind of thought of that. Yeah, and I'm sure you've all heard that kind of often. Oh, yeah, I kind of had that idea. Yeah.
Anyway, I think we will wrap up here, and we have a reception where you can ask Al more questions. So once again, thank you so much.
Thank you. Thank you for coming.